In this lecture, I'd like to speak to you about another approach to looking at the chemistry and structure and composition of material surfaces, but actually a set of measurements that can in fact be used to, in an interesting way, also look at properties of matter approaching more bulk-like extents. And that is measurements based on the measurement of ion fluxes coming from a sample. The technique I'm talking about here today is secondary ion mass spectrometry. Mass spectrometry is, of course, a technique in which we measure the mass-to-charge ratio of an ion. And from that, we can determine information related to its chemical and compositional nature. SIMS is a technique that generates its ion flux based on the impingement on a sample of an ion beam. So we mentioned in previous lectures the use of ion beams as a way of milling a sample to remove material in order to get spectra in order to measure spectra of clean surfaces, or to use it as a way to abrade material to acquire spectra of surfaces that are actually, or interfaces that are buried within a material, to drill into a material and measure surface by surface its elemental and compositional characteristics. In this particular case, we're using an ion beam to do those same fundamental transformations of a sample, but we're also using it as an excitation to elicit the emission of ions, which we then measure. So in this case, we impinge ions on a sample and then measure ions ejected by it. In the next slide, we see an example. We see a schematic depiction of how this event would happen. I like to think of this as being the equivalent of the killer asteroid striking the Earth, sometime around the Cretaceous boundary period and rendering the dinosaurs extinct. A high-energy object comes in, strikes the world, ejecting matter up into the firmament, which then leads to global climate change in a way that destroys the dinosaurs. Well, this isn't quite that catastrophic, because it's a much more microscopic transformation. But the ion beam comes in with enormous energy and then, fundamentally alters the world that it interacts with by ejecting from it all kinds of components. And what you see here is a primary ion beam coming in, indicated in blue. So we see this flux of ions coming in, and out of the sample comes electrons, positive ions, negative ions, neutrals. And these positive, negative, neutral components can actually be of very different and wide-ranging masses. That the energies associated with the primary ion beam are sufficient to actually emit matter in diverse form with diverse masses in broad trajectories. And also we'll see imparted in here, electrons, right? E minus electrons. We're also at energies that are sufficient to actually ionize materials as well. So we have generated in this particular way very complex compositional characteristics. Now, one other part that's actually interesting here, if you'll notice that if you look in the part of the sample which has not experienced beam exposure, the way this is depicted schematically is to show that we have in fact some characteristic distribution of the open circles and the filled circles that might illustrate compositional heterogeneity. In regions where the ion impacts are occurring, as we mentioned in the earlier lecture, we in fact move atoms around. This ion milling also induces ion elicited mixing that will actually jumble compositions. We also inject matter. So even if we have argon ions imposing on a sample, these energies are sufficient to actually inject the argon atoms into the sample where they will be entrained, basically being unable to desorb back in the gas phase because they've actually been injected into the solid lattice of the material. And the other part of it is that the flux of atoms coming out or the flux of atomic components coming out don't necessarily have to directly reflect the composition of what's present in the material, because of the fact that we have to actually look at whether or not the cross sections for emission of all these various components widely range in their magnitude. Now, just to foreshadow something that we'll talk about in more detail, the cross sections for ion emission in this case vary over many orders of magnitude. SIMS is one of the most analytically sensitive techniques that possibly exist for measuring attributes of elemental and composition based variations in materials. However, it is also an incredibly difficult technique to quantify in highly precise ways because of how variable the cross sections for ion emission are. And we'll talk more about that. So this is a very complex physical process. Ions in, lots of stuff happening. And from that comes a fairly rich outcome in terms of analytical capabilities. Now, what I should have mentioned in the last slide, and I'll go back to just to pick up again, ions are a charged particle. Anytime you're working with charged particles, it is in principle possible to envision this as being both a small area analytical possibility, but also an imaging possibility, because what we can always do is take the charged particle, define a beam of it, and then use electric fields as a way of rastering the beam, and then we can then look at this as both a small area analysis, but also a large area imaging-based analysis, much in the same way as what we saw with the use of electrons in the context of Auger electron spectroscopy, right? And so we can lay out a block diagram of a secondary ion mass spectrometer. What that would entail is it would have an ion source. There is just a broad and rich set of possibilities here about of the kinds of ions that are used. The slide says exemplary cases being argon, cesium, oxygen, nitrogen, gallium. However, in recent years, even more complex forms of ion sources are now available. For example, gold-3 clusters, a beam defined by ions of 3 gold atoms carrying a single positive charge. The reason why you would use an ion of that type is that it's actually, using the asteroid analogy, it's a fairly massive asteroid, such that it's a way of impacting a solid with an ion which will deposit energy of fairly large amounts of energy, but very proximate to the collision interface. Okay, and so that's a really interesting and important aspect of this technique. How we can vary these ions. And the other thing I should say is that the ions can, in principle, be both positive ions and negative ions, and that has important characteristics as well. Right, but typically, we would use, for example, like an argon plus ion or a gallium plus ion as an ion source, and then we would impinge that on a sample, and then we have this really important part here, and that there would be a set of sectors that would allow us to both energy analyze and mass analyze the flux of stuff that comes from the sample, and then from that, we can acquire mass spectra. So what would be measured here in the mass spectrum is intensity. That's the number of ions arriving with particular charge to mass ratios. All right, and that's a conventional mass spectrum. Because this is an intrinsically an ion-based technique, depending upon what the ion currents are, we're either drilling slowly into the sample or we're drilling rapidly into the sample via this ion-based milling phenomenon. So in principle, if I sit at a spot, I can actually depth profile by measuring ion yield as a function of time. because ion beams can be focused to a fine probe, and in state-of-the-art instruments, these probes can be tens of nanometers or even 10 nanometers in diameter. That's how fine the spatial resolution can become. I can actually take an imaged ion beam, a rastered ion beam, moving across the sample pixel by pixel by pixel. And in each one of those pixels, I measure spectra. And that would define an image map that defines all the ion contents that are present as a function of XY coordinates in the sample. So that would be an image, but a compositional image. But also, because I'm eroding material in time, I could get an overlay of those images that are actually the sample imaged in 2D compositional maps in depth going into the material. So the more I drill into it, the further I go into it, the more I know about bulk compositions. So surface to bulk. Now there's two words you'll hear used to describe the SIMS technique. One is, you might hear people say SIMS. Typically when they just say SIMS, they're talking about dynamic SIMS. And dynamic SIMS, with some caveats, is principally a measurement that's done at relatively high ion fluxes, because dynamic SIMS is a measurement protocol that's used to look at materials more into their depth. We want to look at matter in its extent, so the ion currents used are higher in order to get information about material more penetrating into its bulk. Static SIMS, on the other hand, are measurements that are rigorously considered to be surface-sensitive measurements, because the measurements are done at very low ion fluxes. And as a result, the compositional information I get is restricted to 2D maps at distances very proximate to the ambient surface of the material. And so, the types of analysis that we might do. And the principal differences being that in dynamic SIMS, you're really doing depth profiling. And in static SIMS, we're really looking at compositional and structural information measured, more of the order of a surface to very near proximate surface layer. And other words that you might hear, for example, like, people might use the word TOF SIMS. That just actually refers to the characteristics of the mass analyzer that's used, TOF standing for time of flight. Okay, so let's look at some rough comparisons. We know Auger spectroscopy uses electrons in, electrons out, spatial resolution, nanometer scale. And very good analytical sensitivity, really good to the order of about 1 atomic percent. XPS, similar in terms of atomic sensitivities. And again, sampling depths, of the order of angstroms to nanometers. Again, areas analyzed, typically more micron scale, and that's typically associated with the fact that X-rays are hard to use as an imaging probe. Because, X-ray lenses are just much more complicated than our lens systems for charged particles. But now here's the part about SIMS instruments. Typically, dynamic SIMS is not a small spot because it's more to analyze matter in depth. But static SIMS can actually be, very high spatial resolution measurements. And here it says 10th micron, but actually very state-of-the-art instruments can push this by more than a factor of 10 higher sensitivity point to point. Now here's where the things are very much different in terms of detection limits. Of the order of 1 atomic percent. That's sort of the limits of electron-based spectroscopies. Ion-based spectroscopies, on the other hand, because of the incredible sensitivity of mass spectrometry, and this is really good to of the order of 1 part in 10 to the 6th. Way more challenging limits of detection, parts per million. And in point of fact, it can actually even be much better than that. And part of the the interesting and challenging aspects of this is if you go to these extremes of analytical sensitivity, is the question of how do you construct appropriate calibration tools to characterize information at such challenging levels of analytical sensitivity. What do you detect in dynamic and in static SIMS measurements? Well, in dynamic SIMS, because we're basically, just removing gross quantities of matter, it's very much a damaging technique. So it really changes information from its compositionally dependent form into things that are more at the limit of the energetic and dissipative processes that are being used to mill the sample. So it's very good for elemental specificity, but it loses any kind of useful attribute related to the molecular structures that might have been present. Whereas static SIMS measurements, time of flight SIMS being a stand-in for that, is much more useful for looking at molecular attributes associated with material systems. And so with this, we see there's like nice complementary characteristics of these two spectroscopies. Now I'll leave these slides to you to look at, just laying out differences in types of instruments. This is an old instrument, but it's still a very powerful one for doing dynamic SIMS measurements. And this is a schematic of a more modern version, time of flight static SIMS instrument. But at the heart of both of these is a simple overlay that was of components, much like that earlier slide, and that is you have an ion beam, you have a sample, you have ion optics that let you do mass analysis, and then you have a detector, which somehow lets you use this either in imaging mode or spectroscopic mode, etc. All right, and because we're doing mass spectrometry, right? What we're doing is we're fundamentally from energy measurements relating that to mass, because what we measure is charge to mass ratio. Now, the quantitative aspects of SIMS. So here's our ions in schematic form striking a surface with all the things coming out. And basically what we want to know is how does that relate to the part of the picture that I'm interested in and that is, I'm asking the question, what is this material? What is this stuff? What's it made out of? How much part A, and how much part B, and, and what I of Newton, and all the other kinds of features that might be present. How do I get that out of mass spectroscopy? Well, fundamentally, we know a few things, with very high precision. We know what the ion is that's going in. We know what the energy that it's carrying with it. We know the beam current. We know exactly how many ions per second are impacting a material surface. And from that, we can actually also measure other things that we know. We can, very precisely measure the flux of ions coming out, and we can measure with very high analytical sensitivity their mass. And one of the things that we actually want to know is what does that mean in terms of compositional information. So, for example, imagine we're dealing with a SIMS measurement that's looking at a secondary ion flux that's composed of many different components. How can I relate that information to its underlying compositional dependence? What I want to know is the fraction of stuff that's present that corresponds to a particular elemental or molecular speciation. And the difficulty here is that there's lots of stuff that's really complicated that kind of gets in the way with it, right? So, for example, you see one component here that's laid out, eta, right? The transmission of the analytical system. There's a machine that's present, and not every ion goes through the machine with unit, efficiency. And so we need to know things about how the instrument works, but that's presumably something that could be, figured out and calibrated. And in point of fact, it is. So the most complex part is the one that relates to the primary event by which the ion is generated. so the primary ion comes in and it generates an ion. We need to know something about the cross section that defines that secondary ion yield. And it turns out that that's just a really complicated and strongly material dependent thing. And that's why calibration is really at the heart of high precision, high sensitivity analytical measurements using this technique. If we're using it as a fingerprint and we don't need to have a calibration standard in order to define a precision-based metric for the measurement, that can be done very straightforward. You detect an ion, there's something present, but we can't say what its composition is. With a standard, we can then begin to do so. Also in complex compositions, we have to think about sputter yields. We come in with a high energy primary ion, and the energy can partition between all the components in ways that are complex. So if I have an A-B composition present in the sample, A and B don't have to be ejected with unit probability. And so I could actually lose more A than B or vice versa, depending upon the details of the ion impact. Okay. And another part that actually has to be thought about here is whether or not we can bring computational things to bear. This is actually an area that's been worked on very hard. That's been worked on in quite a bit of depth, but it's really very hard to theoretically predict sputter yields because of the fact they are so chemically and compositionally dependent. Okay. So we can look at what these sensitivities are. Ion yields will vary with what are called matrix effects. Okay, and that is how the surrounding host of atoms influence the creation of an ion, which is then expelled from a sample surface and finally detected. That's an important attribute. Part of it is an interesting feature. Some materials actually actively segregate components at their free surfaces, right? So these surface segregation effects actually could be an important property of a sample. So, we might compound a material to give it improved resistance to and stability in air, right? For example, plasticizers and antioxidants. If those materials dissolve into, or for example, flame retardancy in a polymer, depending upon where those materials accumulate, they might segregate. They might dissolve into the polymer, be stably dispersed in it, or in fact, they might actually segregate to ambient interfaces. We would detect them in high concentration in SIMS because of the fact that they're not homogeneously localized. And of course, many other things come into play as well. But, here's the important point, that sputter yields can vary by many orders of magnitude. And that's what generates some of the interesting components. There's actually another part as well. So, for example, sputter yields will also depend upon the nature of the incident ion. It's not just how much kinetic energy is the ion carrying, but also some features about how it actually changes the chemical ambient that's responsible for the emission of the secondary ion that we finally detect. And so this is actually a place where you would go to the literature and say, this is the nature of my sample, and what sort of primary ion should I be using to best advantage analysis of this class of material. So here's a periodic table that's denoted for its best association with a particular cationic primary ion source. For example, an O2 plus or a cesium plus primary, and in one case determine measuring a positive secondary ion, in another case measuring a negative secondary ion, right? So this is a way in which you would use very different kinds of instrumental protocols, right, to improve sensitivity for carbon and nitrogen-based compositions, or boron, using in one case a primary oxygen ion, or in another case, a primary cesium ion. So it's a really interesting thing. And this is, you know, a rich recipes that are out there, a rich set of recipes out there in the literature that you can use to improve the analytical sensitivity of your measurement. Now here is a plot of relative secondary ion yields, and again here measured for two different kinds of primary ions, cesium plus and oxygen negative ion, and detecting in one case negative secondary ions, in another case positive secondary ions, and then looking at, you know, the relative elemental sensitivities. And I think the thing is, it's not that these things go up and down, right? They go up and down and whatever, but it's just the, you know, the magnitude that shows on the y-axis here. You'll notice that these ion yields are varying by orders of magnitude. These are log scales here, right? And we're seeing many orders of magnitude. And so, you know, just going from, you know, beryllium to nitrogen, right? You know, on this one plot, right? You can see, you know, almost 4 orders of magnitude change in sensitivity. So, I mean, these are, you know, phenomenal differences. And so this is part of, like, the science, but it's also really very much part of the art of using this technique, because you have to know something about this in order to ensure the best analytical outcomes. And again, you know, on and on and on. You can spend like almost forever, you know, mapping you know, a parameter space for this kind of analysis. So let's talk about a really, you know, neat kind of measurement that this kind of a protocol very fundamentally advantages. So there's actually shown here a schematic depiction of a multi-layer sample. That's this is the kind of things you would find in electronics. These are MBE grown compound semiconductors. MBE standing for molecular beam epitaxy. And this is gallium arsenide in each case, but gallium arsenide with different kinds of dopants. So these layers are modulated with dopant atoms. They're dilute compositional impurities which modulate the electronic structure in spatial extent based on the inclusion of either carbon or silicon based impurities, right, which are deliberately put in with very precise concentrations in substitutional form, right? And actually, what's shown here is a sputter depth profile in which all the components of this are measured, but one really funny one, which isn't actually specified in the layer that's shown there, and that is via the growth sequence, whether or not there's been the incorporation of hydrogen within the semiconductor levels. Now, hydrogen is a very hard to detect atom as a substitutional or dilute compositional component in a crystalline solid. And there's a few techniques that let you do it, but this is a really powerful example of it being done using a mass spectrometric method. And what you notice is that in all the regions associated with several layers of the carbon-doped region, that there are, in fact, you know, significant densities of entrained hydrogen atoms that are also present in that phase. And we also can see, you know, for example, the anti-correlated silicon composition of this other component. And then finally, you know, we reach the bulk gallium arsenide substrate, which has neither of these dopant-related characteristics. Here, in fact, we see something that's relatively more surprising, and that is the change in compositional profiles that comes from a form of thermal processing. And there's a lot of detail that we could go into here, but notice, like, for example, in the first layer, the hydrogen content is depleted because that hydrogen just, in fact, diffuses out of the sample and is lost as hydrogen gas via bimolecular recombination and absorption as H2. And the other point here is that if you look at in this blue part, we notice that the compositional profile associated with the silicon is changed. It becomes broader because the silicon component is actually interdiffusing into the carbon-doped region, right? So that interface between those layers is becoming graded as it's heated, even at relatively modest temperatures of the order of 400 degrees Celsius. So this would be a very hard kind of piece of information to get, how a dilute silicon component, right? This is like, you know, really small numbers of silicon atoms per cubic centimeter, actually being measured with very high sensitivity, and its spatial distributions being changed as a consequence of thermal processing. Okay. Mass resolution. The mass analyzers used in modern instruments are incredibly high. And I think this is a really, beautiful example of just how high this analytical resolution can be. This is essentially a measurement made at a charge to mass ratio of 32, and it's actually done at a charge to mass ratio of 32 and then some, right? And that you're actually looking at a signal that's coming from a mineral. This is pyrite, otherwise known as fool's gold, really beautiful mineral. Looking at a small grain, but at a mass that corresponds to something that you would be very hard put to say, does this actually correspond to the sulfur content or something else? And if you looked at this in something other than high resolution, right? And there's two different ways of doing this. This is looking at it in a straight ion count way. That's a linear mode detection. This is a logarithmic way. This little bump here actually corresponds to an O2 component coming out of it. There's actually an ion flux that's coming out of the sample that actually corresponds to the negative anion of diatomic oxygen, right? So that's and you can see that the difference in mass here is very small, right? It's of the order of 2/100ths of an AMU, right? So mass analyzers are not only high sensitivity detection elements, they're also very high resolution detection elements. And because of this feature, it actually allows you to do, some pretty, spectacular measurements. I won't go into the details of what this slide shows, but actually, it's a kind of a thing that is very important, for people that look at like how thermal environments, impact properties in complex hierarchical material structures. And this one is very much looking at the oxidation of a material, but it looks at it from the point of view of trying to understand the mechanism associated with the motions of atoms in the solid state that lead to its thermal transformation. So this is an example of what's called a superalloy, nickel-3 aluminum. It's one of these really high performance, high temperature resistant materials. Because of the high nickel content, very useful in oxidizing ambients. But at high temperature, this material will oxidize. And one of the ways you could do that is by doing graded oxidations, changing the isotopic content of the oxygen that's contacting it, and looking at how an O18 label and an O16 oxygen, how those materials move in time as the processing occurs. And so, for example, you look at the characteristic interface that's shown here, would allow you to see, in fact, that there's one atom type or another atom type moving in the material. So do oxygen atoms move in, or do nickel atoms move out, right, when you oxidize this material? So experiments like this actually let you do measurements of that type. Depth profiling, again, to illustrate the issues of dynamic range. This is a modulated doping scheme for silicon that's based on boron dopant, a boron dopant. This is actually using diborane. That's I don't know if anybody's like hasn't worked with materials like this. This is like one of these like really super scary compounds because it's just so incredibly pyrophoric, as is disilane. Again, a really, scary compound. So, the kinds of protocols that have to be used to grow atomically precise materials using these kinds of feed gases are very stringent, right? But in proper environments and with good laboratory protocols, you can grow things of this type. And in fact, what you notice is that the fluxes of the gases actually determine the compositional outcomes, right? And so we can follow dopant profiles, right, from here to here that vary by 3 orders of magnitude, right? And so this gives you a very rich and powerful way of looking at dopant levels in semiconductors, and this can be carried over much more broadly into other classes as well. Okay, so I'm going to skip this slide because it's just more detail in this form, but I will mention the following thing. Again, by looking at the issues of like how this measurement goes, and with the final caveat, we have to be very careful with how you look at sputter depth profiles from the point of view of whether or not the interfaces you're looking at are truly graded or in fact reflect the impacts of the ion beam milling that's being used. And this slide is just calling out that that important point in a very powerful way, to say that when we look at these compositional profiles, we have to be aware of what the ion beams are doing, and in point of fact, that we can in fact improve the sensitivity by paying attention to the instrumental features as well. Like, so for example, we're looking at the detection of a carbon anion and using a particular source gas, but what we do is we change either the kinetic energy or the angle, and that actually impacts the energy transfer, and that would change the characteristics associated with the ion beam induced interfacial mixing. So we can actually use that in a fairly important analytical way. Now let me finish by just doing a quick go through of some of the other capabilities that can be done using that can be carried out using SIMS. So this is an example of an imaging-based protocol. So here's a SIMS measurement that's actually overlaid on top of the grain structure in a vanadium based steel sample, right? And what you're looking at is basically segregation characteristics associated with particular components. And what we're asking in this experiment is, where do these components go? So sulfur is a relatively low content in this metal sample, but you notice that it is in fact really strongly localized at the grain boundaries, right? And other components, are like for example, oxygen impurities are more diffusely distributed. You notice that in point of fact, it may be localized more in some grains than others, so there might be a more complex issue here associated with background. But you notice that these intensity differences are actually correlated against the vanadium content. So this is a granular structure, but there's also embedded within it, strong, from an atomic perspective, strong compositional heterogeneity. Okay. And finally, I want to say, what are ways in which we can make the analytical measurements, other than just saying, ion yields can vary by many orders of magnitude. in particular cases, there exist protocols for doing very high sensitivity calibrations. And so let's just look at the case of semiconductors as an explicit example. There are methods that you can use ion beams that are highly precise to generate samples very much similar to the cases you're trying to measure, but that have very precise compositional contents that allow you to then calibrate your unknown measurement. So this is an example that was done using a implanted silicon single crystal that had been implanted using phosphorus, using a very precise implant energy and dose. Right, so the implant was made at a kinetic energy of 100 kiloelectron volts. So this is a very high energy ion beam, which is then used to implant phosphorus into the silicon sample. And you can then use that material as a way to calibrate phosphorus as an impurity in an unknown silicon sample, right? And so these kinds of approaches, so this kind of implanted sample might cost you about, well, the last time I did something like this, it cost us about $10,000 to make the sample. So while this is possible, you might not want to do it. And if you're a graduate student, I advise you to talk to your professor about whether or not you're going to spend $10,000 on an analytical standard. Okay, and so this is more or less the quantitative details, and I'll leave that as supplementary material. And then, just to finish with the summary overview, the difference between dynamic sims and static sims. Well, in fundamental terms, we're measuring very much the same thing. Ions in, ions out. And what's really differing is that in the one case, we're eroding the sample in order to look into its compositional features in depth. In the other case, we're putting in ions slowly enough in order to affect very little compositional change. So one looks at matter more in its extent, and the other is rigorously a measurement of surface and interfacial properties and composition. And with that, I'd like to thank you